Hello, Senior Seminar of July 2017. This is Zachary Everson. I'd like to present my paper on the sustainability of dirt. Sustainability of dirt began with agriculture. That's when we started using dirt or soil as a resource. We didn't know what was going on back then when the plants would stop growing because the soil was depleted of nutrients. All we knew is the plants stopped growing and we would move on to greener pastures. Soil science, the first sign of some kind of soil science is from China 4,000 years ago when they classified the soil for the purposes of taxation and stuff. So they were at least aware that there was different qualities of soil. In the Western world, the first sign of soil classification came from Great Britain in the 18th century. In the 17th century, we started, really getting into chemistry, geology, geography, some of the sciences that are the basis for soil science today. Those sciences had a hard time kicking off because of religious resistance to science at the time. In the 19th century, we kind of got past the religious resistance, and we started figuring out that soil needs water, carbon dioxide, and nutrients like nitrogen and carbon in order to grow plants. That those things were the basis for growing plants. We figured out that irrigation, tilling, fertilization, practices like that could provide those things, could provide nutrients, carbon dioxide, and water. And so we started viewing soil as an inert supportive matrix to be flooded with nutrients. This is kind of how we see it today too. We're kind of starting to just begin to see it as a non-renewable resource. When we started fertilizing and tilling and irrigating, our crop yields just went through the roof, and that's kind of what we're living with right now. You can go down to the store and buy all sorts of food from all over the place, thanks to very high crop yields, and they're just getting higher and higher with more science. But this is leading to a false sense of security because we're not thinking about, when we're producing so many crops, we're not thinking about what's happening to the soil. And the soil, of course, is the basis for those crops. So first I want to talk about what soil is made of at the most basic level. This is when it really started getting interesting for me when I took soil science, and why I wanted to present on this topic. Soil is made up of minerals and organic matter. Minerals come mainly from the rocks, from granite and, the geology that is weathered or broken apart into, little particles are broken off of the rocks, and that provides the mineral basis for the soil. Organic matter can also, I was surprised to find out, turn into minerals eventually if it's digested enough times, which brings me to organic matter. There's two different ways of looking at organic matter in the soil. We have living organic matter, which is the bacteria, the fungus. Most of it is microbiology. There is also macrobiology, such as worms and bugs and things like that. But mainly microbiology that decomposes the dead organic matter. Dead organic matter is anything that was living and died and is now part of the soil. From dust we came, and to dust we shall return, that kind of thing. So plants, animals, etc. And these are decomposed by the microbiology and even some of the macrobiology. There are 5 factors to soil formation. There's actually 6, but the first 5 factors are climate, parent material, topography, organisms, and time. And then the 6th is unspecified factors, which is obviously very unspecific. The biggest part of that is human activities. This is something that is becoming more and more of a factor to soil formation or soil erosion and depletion. Soil is not really a renewable resource. It does renew, but it takes thousands of years to weather those minerals off the rock, thousands of years of microbiology decaying, organic matter. We're using it at a way faster rate than it is able to replenish. We're using as much of the surface of the earth as we can, and we're not allowing it to replenish, and so we've kind of made it a non-renewable resource. There are 5 classes of soil particles, and we'll talk in a little bit about why this is important. The largest size is stones or gravel that's greater than 2 millimeters. Then coarse sand, fine sand, silt, and then clay is the smallest. And clay plays a very interesting role in soil formation and soil structure, as we will find out later. Why is particle size important? One reason it is important is because the particle size determines the pore space. The pores are the space in between the particles. So when we have large particles, we have large pores. When we have small particles, we have small pores. And then why is this important? Pore size determines the soil's water carrying capacity. So large pores allow water to kind of leak through more easily, and small pores kind of capture more water. It's kind of like a sponge. The greater pores don't do as good of a job of holding water, and the smaller pores are a better sponge that hold the water better. This is through surface tension. So when you have larger particles, you have surface tension around the particle, and you have lots and lots of space in between the particles. With the smaller particles, you have way more surface area for the surface tension of the water to hold on to. In real life, soil is not really uniform a lot. Maybe, in the desert, healthy soil is not uniform. Healthy soil is made up of clumps. You want your soil to clump, and the reason it clumps is because of the organic matter and the clay holding it together. Healthy soil has healthy clay and healthy organic matter that hold the soil together in aggregates. There are 2 different types or sizes of aggregates. Macroaggregates are, the larger clumps, and they have an effect on the health of the soil. They hold a lot of the organic matter that provides the nutrients to plants and whatnot. Microaggregates make up macroaggregates and are held together by organic matter, kind of like glue. Here's a picture of a microaggregate. It contains clay particles, or clay domains actually, silt particles and sand particles and organic matter. So it has mineral particles, but not really so much gravel or something like that, because microaggregates are small. Clay particles, in this sense, I'm going to call them clay domains. So individual clay particles don't really hold anything together. Clay particles hold ions, and a healthy clay particle holding healthy ions is going to bond together with other clay particles into clay domains. The clay domains are going to help all the organic matter and stuff and minerals stick together to form microaggregates. And then when you have larger organic matter, that helps make macroaggregates, and that's your healthy soil. So you have little clay particles that are held together by ionic bonds. There's 2 different types of ionic bonds. There's ionic particles that are attracted to the clay that have 1 positive charge, a single positive charge, and there's ones that have a double positive charge. The particles, or the ionic particles, that have a single positive charge do not form flocculates or clay domains. When you have 2 positive charges, that creates, that bonds together to make flocculates, which is the clay domains that I have been describing. We kind of already went over this. Organic matter is made out of the dead plants and animals and microorganisms, and the living microorganisms, and even some macroorganisms that decompose the dead organic matter. This is kind of a continuous cycle of decomposition. So, it's not just decomposed into humus. It's decomposed into more dead, slightly decomposed organic matter, and over again until it becomes humus, and then eventually it might even mineralize if it's decomposed enough times. It passes through the digestive system of different microorganisms over and over again. Here's an interesting little picture of the soil food web. So, You have plants that feed on the organic matter, and then you have bacteria and fungi, and those feed on the organic matter as well, and they provide food also for, arthropods, and then up the food chain. All terrestrial life depends on soil. By definition, of course, terrestrial means land, and soil is hopefully part of the land. Sometimes there's less soil and more rock, but soil provides nutrition to plants, and plants provide nutrition on up the food chain. It also provides nutrition, of course, to microorganisms and small macroorganisms. It also provides structure. So soil provides a foundation. Sometimes people even use it as a building material, building bricks and things like that. And then soil also depends on terrestrial life, because healthy soil has dead organic matter, and dead organic matter comes from terrestrial life. Soil also filters water and air. This is a very important role that it plays that we are more recently figuring out. Improving air quality. Healthy soil actually sequesters carbon. Unhealthy soil that holds carbon lets it into the atmosphere. So we want to keep our soil healthy so that we can sequester carbon dioxide in the atmosphere instead of adding to it. Here's kind of a little graphic. I'm kind of running out of time here. That shows that it releases CO2 in the atmosphere. Soil releases CO2 in the atmosphere. Plants, which depend on soil, take in a lot of CO2 out of the atmosphere. They can hold it in their structure. Soil also holds CO2 in its structure as long as it's healthy. Soil health is measured by its capacity to produce resources. If soil is not producing resources, then it can't be considered healthy. And again, those resources are food and structure, water and air quality, and plant and animal health in general. We tend to think of soil as a matrix or a resource for food production, and that's really taken it for granted as a way to filter pollutants and filter and sequester carbon and things like that. Some of the problems with unsustainable use of soil, we end up with erosion, loss of fertility. Those are the two really big ones, and then more hidden are the reducing air and water quality. I think we've covered that a little bit. Things that can cause problems with soil, that can cause unsustainable soil use, are overgrazing, land clearing, salinization, desertification, and overfertilization and pesticide use, which also helps pollute the water. Agriculture is the most widespread contributor to non-point source water pollution in the U.S. because of the excess use of fertilizer and pesticides that produce that great amount of food for the increasing population. We know that food needs of future populations, because we just keep populating at an ever-increasing rate, are going to require a doubling of crop yields. So as much crops as we're producing now, and as unsustainable as that can be, we're going to have twice as much very soon. Before we start demonizing agriculture and farmers, we need to realize that agriculture is very important. It's important to the farmers. They are the stewards of the land. They depend on it for their livelihood and their communities as well. And all of humanity depends on agriculture so that we can be fed. Scientists who are concerned with soil quality also need to be thinking about food production. And land managers who are concerned with food and other production also need to be concerned with soil quality. They need to start working together, and I don't think that we've done a good job of that yet. That's kind of the next step. We started in soil science with kind of realizing that soil needed nutrients and carbon dioxide and water, and we figured out how we can put those things in the soil. Now we're learning that there's a whole microbiological ecosystem in the soil that provides soil health. Looking to the future, we need to incorporate all these different sciences, agronomy, ecology, chemistry, physics, etc., so that we can be thinking about soil sustainability and production together. Thank you, class. It's been fun. I'll see you all on the flip side.